Equations are a lot like this seesaw. Whatever's on the left side has to be equal to whatever's on the right. Now, to keep it balanced, we have to do the same thing to both sides. There you go, buddy. See? Still balanced. But if you don't do the same thing to both sides, your equation is out of balance and no longer equal. Ouch! You can keep equations balanced by performing the same operations to both sides: addition, subtraction, multiplication, and division. Use any one of these with the same numbers, and you'll keep your equation equal. Let's say you have a big box of markers, and your little sister needs to borrow some for a project she's doing in social studies, a diorama of the 7 wonders of the world. She picks through the markers and takes 12 of them. Now, you want them back. You've been collecting these markers since 2nd grade, so you say to her, "When you're finished, put them all back. When I check, there better be..." And then you realize you don't know how many you started with. So you quickly count the remaining markers, and there are 34 of them. How many did you start with? We can write an equation to solve this problem. As with many equations, you want to tell the story in numbers and symbols. In this story, you began with a box of markers, but the number of markers is unknown. So we'll represent that number with x, and we'll let x equal the total number of markers. Then your sister took some away. That's subtraction. There's the subtraction sign. She took 12 of them, so it's minus 12. And now the number of markers is equal, so there's an equal sign. The number of markers is 34. The equation tells the story from left to right. The number of markers minus 12 is 34. And we want to find how many markers we started with. We want to solve the equation. We want to solve for x, which is the number of markers. To solve for x, we need to isolate the variable. Get the x by itself on one side of the equation. To do this, we're going to perform what we call the opposite operation. Now, addition and subtraction are opposite operations because if you add, say, 5 to an amount, then subtract 5, the amount doesn't change. Multiplication and division are also opposite operations. This equation has subtraction in it, so the opposite operation is addition. Let's add 12, not just to the minus 12, but to both sides of the equation, so that, like the seesaw, we'll keep it balanced. When we add the positive 12 and negative 12, the result is 0, and x plus 0 is x. On the right side, we add 34 plus 12 and get 46. So, x equals 46. We should check to see if our work is correct. Since x equals 46, go back to the equation and replace the x with 46. 46 minus 12 does indeed equal 34. So, x does equal 46. Remember, the x represented the number of markers we started with. So we started with 46 markers. So there better be 46 markers in that box, little sister. The same approach can be used with equations involving other operations. Let's say you're selling tickets for a school dance. You start out with $49 in small bills in the cash box to use as change. Then you sell some tickets and put all the money in the cash box. At the end, there is $310 in the cash box. How much did you collect in ticket sales? And notice, we don't put any dollar signs in the equation. We need to subtract 49 from the left to isolate the x. So we'll subtract 49 from both sides to keep the equation balanced. 49 minus 49 is 0. So we're left with x by itself on the left. 310 minus 49 is 261 on the right. So x equals 261. Check your work. 49 plus 261 does equal 310. Therefore, x equals 261. Remember, x represents money, so you sold $261 worth of tickets. Good job. 8 members of the French Club want to hold a fundraiser to collect money for a trip to Quebec. They've agreed to take all the money and split it evenly so that each member of the group gets $425, which is the cost of the trip. How much do they have to raise? Let X equal the money that they raise. Then X will be divided by the 8 club members, with the result being $425 per student. To isolate the X, we need to eliminate the 8 by using the opposite operation of division, which is multiplication. We'll multiply both sides by 8. That balance thing again. On the left, the 8's cancel, leaving us with X equals 3,400. Perhaps putting the 8 over 1 will help to show that this is a lot like the canceling process you use when multiplying fractions. However you arrive at the solution, take the 3,400 and substitute it in the original equation to check your work. So X equals 3,400. That means the club needs to raise $3,400. That's a lot of candy bars and car washes. A school would like to purchase notebooks for all 216 students taking algebra. The notebooks are sold in packages of 4, so our equation has to reflect how many packages of 4 notebooks must be purchased so that each of the 216 students can get one. X is the number of packages. 4 is the number of notebooks in each package. Once again, to isolate the variable, we perform the same operation to both sides. In this case, division, the opposite of multiplication. When we divide the left side by 4, 4 divided by 4 is 1, and 1 times x is x. 216 divided by 4 is 54, so x equals 54. You know the drill. Let's check our work by substituting 54 for x and showing that 4 times 54 equals 216. So x equals 54. That's 54 packages of notebooks. If the number multiplied by the variable happens to be a fraction, you must still divide both sides by the fraction, but remember that dividing by a fraction is like multiplying by its reciprocal. So instead of dividing by 2/3, multiply both sides by 3/2. Cancel the 3's and the 2's, and 24 times 3/2 is 36. So x equals 36. Don't forget to check your work. 2/3 times 36 is 24. So x equals 36. So when you're solving equations, isolate the variable by performing the opposite operation. But be sure you do it to both sides. That way you'll always stay balanced.
Yay!